So good morning. So today we begin our study of statistical mechanics, and we begin with a model which we'll call the ideal gas, and we'll explain what is ideal about it. And so, so the ideal gas is just a collection of n non-interacting particles. Okay, we make them identical also. Same species. We can have multiple species, but for now we'll just do something in a box. Okay. So the first thing is, let us, what does it mean? So if you were doing classical mechanics, the dynamics would occur in phase space. Which is xn dimensional, right? Because we have positions. So R1, R2, Rn, and momenta P1, P2. Right? This is what we know. And when we said non-interacting, and you see there are no forces, so we would write H equal to sum over I equal to 1 and di square upon 2m, where m is the mass of the particle. Okay, so this is what we mean. And but so and we would write these things, but we are ignoring an important thing, which is collisions. Okay, these do happen because we are ignoring collisions. Actually, they are important. Okay, we'll see in what sense they are important, but so and not present in the above Hamiltonian. Right. So let's just do a little bit of a thought experiment. If there were no collisions, each one is a free particle. So if you start out with the particle at, pick a particular particle, and then you give let's say, look at its momentum. Its momentum is a constant of motion, but that cannot be. Okay, so there are two types of collisions among particles and with walls also of the box. Right, so these are two kinds of collision. So let's first take a single particle, and if you it'll be its momentum would be conserved, but that would be the free particle moving out in space, but it's in a box. So first thing that would happen is when it hits the wall, its momentum changes. So every collision with the wall changes the momentum. So you will see that that there will be discrete jumps in the trajectory of the thing, which we have seen for particle in a box. We have already seen elastic. We'll assume they're elastic, so there's no loss of energy. Okay, so similarly, if there are two particles, they can collide and they will again go off. So you can see that what you would have thought as a single trajectory will get mixed up. Okay. So this can happen, and so collisions have this. So collisions. Okay, this is what happens, and so this way, so we'll just keep this in the back of your mind. We'll come back to it a little later. But for the moment, we'll just see that that the Hamiltonian is just the sum of all the individual energies for Hamiltonian. Okay, so that's what we have, and so. So let's just do a little bit of in quantum mechanics. Suppose the box was cubical. With side L. Okay. Then the energy levels are given by epsilon naught, which we wrote last lecture, which was h square. So epsilons for each particle that would be given by epsilon naught times n where n1, n2, n3 are the quantum numbers, and these are they belong to positive integers, non-zero positive integers. So now quantum mechanically, if you assume that every particle is in one of these eigenstates, then the energy would be some okay. So there will be how many quantum numbers? 3n quantum numbers. And this is the same as the degrees of freedom. So this is what the quantum mechanical thing is. Okay. So first thing is, so now we want to discuss this thing in statistical mechanics. And so the key is that we'll assume that this energy is specified in this narrow range. Okay. However, so the range is so the width of the range is delta E, but the point here is that typical spacing it will be of the order of epsilon naught. So we will assume that even though delta E might be small, but is much larger than epsilon naught. Okay, so what that means is that so let's say we have energy is increasing this way. So this is E, and this is E plus delta E. So what that means is many states, many eigenstates fall in this region. Okay, and do a good approximation. We can treat E as a continuum variable, as a continuous variable. Is this clear? Hello? Am I audible?
Yes, sir.
Good.
Yes, sir.
Okay, so this is so delta E will be pretty small, but it's just compared to epsilon naught, which is just the energy scale of one particle. Remember, E will be, E is the sum for all of them, so it will be at least capital N times epsilon naught. So it will be large, and so what we are saying is that it will be greater than that, of course. That delta E is small, but not so small. It's not comparable to epsilon naught. So the macro state is specified by three numbers. E, N, and B. Okay, so that's also delta E, but I'm just writing out what are all these things. Okay, E and maybe E plus, and let me not write delta E. Okay, so it's specified by three. And the last lecture we asked questions like what, how many and what is the answer? We saw a semi-classical answer, which said that an integral over phase space okay, energy is the only constraint, right? And particles are in the box. Okay, but this is not the we have to do something to this volume in phase space to get a number. What is it I have to do?
Divide by that small volume.
Yeah, divide by what?
H to the power 3n.
H power 3n,
3n.
right? Because we have 3n degrees of freedom. Okay, so this is a semi-classical. Okay, so let us try to do this thing. So what does the integral d cubed xi integral give?
L cube.
It gives
L cube.
volume V. Okay, so L cube was just was an example because I want to write a proper formula. We don't need for the semi-classical computation. We don't need that detail, right? So each integration over d cubed x will give us a volume. So, but how many such integrations are there?
N.
There are n of them, right? Okay. So now what we can do, we have only one constraint which says that, so the constraint now on terms of momenta is that the energy. So let us, yeah, so constraint is that the energy, that is summation, this is the constraint. Okay. So we just have to work out what the this thing would be. But this you can see is that this equation is that of a sphere which is how many? There are 3n of these guys. So it's a 3n of radius actually it's a shell, right? So let me, this is not correct. Okay, with radius in the range is that correct? Okay. So, but you can see that in just simple dimensional grounds, that this this thing, I'll no longer do equal to. So, okay, I'll do one step. So I'll keep it equal to. It is v power n h power. Okay. So this will become p power 3n minus 1 dp d omega of a sphere which is of dimension 3n minus 1. This is what, this is analog of spherical coordinates, right? Spherical polar. What is the question? A shell with thickness. Three n is just is a dimension of the space in which it is. 3n minus 1, it's one constraint. So, so you're saying it's a solid, yeah. Correct. So it's a, yeah, you're correct. So what it means here is a spherical, solid spherical shell. Okay. So this again, so the constraints will be only on this guy, and and this will give you some number. This will give you the volume of a unit sphere. That is some number. So now I will no longer do this. I'll write some proportionality times. This will be proportional to root 2me power n minus 1 times 2me. I'm just doing dimensional analysis. So if you did, we can do this kind of integral up to some factors. This is what we will get. And so now we get something. So we get rho of E, the density of states is proportional to V. It depends on H also. And it also, n power is 3n. Okay, this should have been delta E. What did I do here? 1 second, let me just get my dimensions correct. So I should get a dp, which is correct. So 3n by 2. So I just want to 3n by 2, that's all, and times e power okay. So this is what we get. Okay, so we are able to estimate how many states. Okay, there's no delta E in the. So this is what we get. And this is, of course, as we discussed, monotonically. Okay, so the idea here is we would like to study the. So we would like to. So we would like to, and so let's introduce some notation. Omega of E, which we will write like this as rho of E delta E. Okay, so this will be the number of accessible.
So your screen is gone.
Yeah, I know. So there is this trackpad on my computer, and what happened was that I accidentally touched something and it did whatever it wanted. Okay, so this is just okay. Now I think it won't happen. Number of accessible. Okay. So what I want you to appreciate is that this formula is dependent on all the properties of the gas. It has the volume, that's the energy, total energy, and even the mass is appearing. So these are kind of nice. So this function knows about the macroscopic quantities. That's all I want to say. Okay. So now so it's at. This will be the starting point. Okay. And so we will need some working postulates. So we will discuss a couple of postulates. Okay, so but of them only one we will use a lot. We will need some postulates. Okay, so the first postulate 2, we have already actually discussed. But still, postulate 1 is the following. Okay. So before I even proceed here, so you can see that in this computation, we did not use any collisions, nothing. We just said that it takes values. It's a bunch of points. Every point in there, we broke it up into cells, etc. But first thing to notice, to remember is that even if they were free particles, I mean, they're not static, right? So if you put it in one point in a cell in phase space, it's going to keep moving around. Okay. But further, there are collisions, there are elastic collisions. What they will do, they will change the point in phase space. So what is happening is that basically all the cells in phase space get accessed in some form because of collisions, etc. If there were no collisions, then you might find that it will pick up only one subset, okay, which would fall into the trajectory of that thing. Okay? But now, because of collisions, that is not true. It will be actually, it will think of this. All points in the shell will get accessed as a function of time. So this is something which so collisions are important in doing this mixing stuff. Okay, it's called mixing. Okay, so you can see my slides, right?
Yes, sir.
Okay. So postulate 1 says the following. So consider an isolated system like our ideal gas. All particles are restricted in the box, and so there's no more particles cannot leave the box. Energy, okay, so no energy, mass is exchanged. With the rest of the world. Okay. So now, if the system is found with equal probability in each of the accessible states, at some initial time, it will remain so. Okay, so this is just a statement that if all accessible microstates were happening with equal probability, then it will remain so for future. Okay, so we're not going to prove this. We're just going to say it's a postulate, and but remark is plus Liouville theorem. Have any bearing? Have any bearing? Answer is yes, of course. Okay, so and we will also mention thermal equilibrium. It says that the probability of finding any accessible, finding the system in any accessible macro state. Any accessible macro state is constant in time. Okay, so this doesn't say that the probability has to be equal. Okay, that is a different thing, and that's key. Okay, so the key postulate is postulate 2. Which says that it's little bit, if a system, an isolated system, is found in let me get my language correct. If an isolated system is such that all accessible microstates are not equally probable, at some time, then it tends to approach equilibrium. Such that all accessible microstates are equally probable. So this is a statement about even if you're away from equilibrium and you let the system, it's isolated and you let it reach equilibrium, once it reaches equilibrium, it will be such that all accessible states are equally probable. And then postulate 1 will say once it approaches that, that will remain so. Okay, so and in sort of axiomatic statistical mechanics, this postulate has been proven assuming certain properties, and mixing is a very important property. Chaotic, so it's not chaotic, but it's mixed. I mean, need not be chaotic, but mixing is sufficient. Chaotic is useful, but mixing is milder than okay. Is a milder requirement than chaotic. Okay, so this is what it. So this is the thing. So we will be doing. We'll assume. So our systems. So the conclusion is that we will assume such that all accessible states okay. So I'll pause here for questions.
Sir,
Yeah.
will this be true even if we take like include quantum mechanics?
Yeah. This is
Because
yeah.
like different energy eigenvalues will have different probabilities of getting into, right?
No. So we can go back to that, put it in a cubical box, etc. And so you will say that you might say that okay, the particles are having these. This is the distribution of the eigen numbers among the 3n particles. Okay, but what will happen is that collisions will change the story, right?
Oh, Yes.
right? I mean, so if there were no collisions, what you're saying makes sense. Okay, but there are collisions, and we are ignoring that. And what does collisions do? It makes collisions actually redistributes the energy. And what we are
Okay.
saying is that redistribution is good enough to make, say, to such that all possible things are accessible. Okay, all accessible. So everything. So going back to the thing, so there will be some shell like this, right? So every point or inside the shell will be equal. So a priori you may have thought, oh yeah, I started with a particular point, say X here. But then it's going to get, and that could have a trajectory. So there will be some line like this, right? So there will be something like this. And but that what will happen is that collisions will make it spread out. Any other question?
Sir, is there any example of a system in thermal equilibrium for which all
I can't hear you.
microstates-
1 second. Let me change my volume. Repeat your question.
Is there any example of a system in thermal equilibrium for which all microstates are not equally closed?
Yeah, so you got to have so now you go back to the assumptions, so that you should look for systems which are not, don't have mixing, etc. So you need to have some special properties in those stuff. Okay, but what we are saying is generic. Okay, so those cases have to be treated separately, and but you'll see that this is more normal. Okay, so for this course we'll assume that this is the case. Offhand, I don't know of some. I'm sure there is some Baroque example one can look up, which will do what you're saying. But there could be some mistake we could be doing. There might be some other constraint which we have ignored. And so in our what we thought was the accessible space set of values, there is some things which are not possible. There is some conserved quantity, some global conserved quantity or something. Then you will have to put that in. Okay, that's more common. So it's inaccessible because of some global constraint, which will be, that's more common. Okay. So once we have this thing, so yeah, so there's also a word which goes like, it's called the ergodic hypothesis. Which can be proven, which says that it will all ergodicity means it will visit every possible thing. Okay, so that's what ergodicity means. And so ergodic hypothesis says that even if you start out with your system, like like I told you one example where, let's say we pushed all the particles in one corner in the volume. Okay, so now at some initial time, but you know that if you wait long enough, they will spread out, and the distribution of the particles inside the volume will be uniform. Okay, so that's the kind of so statistical ensemble is this mythical collection. So you make copies for each box equal to one accessible microstate. Okay, that is the thing. So I put 4 boxes because I cannot draw. Okay, so now, so any measurement any actually macroscopic measure is mimicked by taking the average of that quantity measured in each accessible. This is how you go ahead and do computations. Okay, is this point clear? Okay, and equilibrium. So this is the ensemble average. And in an equilibrium, ensemble average will also be equal to, which was our first definition of equilibrium. Okay, so you can do both things. So either you sample in time or you sample these things. So this is what, so but in statistical mechanics, what we will be doing is we will do ensemble averages. Okay, so that's what we will do. Okay, so again, I'll pause here for any more questions before we set out to see how we can make use of this. Okay, so no questions. So now that's a problem, and we'll address it. Isolated systems. I have to find. Okay. So how can we handle such systems, non-isolated? Right. So, for instance, we could put things in a box, but we cannot stop, the system from exchanging energy with the wall. I mean, exchanging energy with the system, the surroundings, the walls, etc. We can't really handle that, and we can't stop those things. So we have to somehow figure out how to do this. Okay? And so that's what we're going to do next lecture. But we will start. We'll do it in the following way, which you will. Okay, so what we will do is we will think of our system. Let A denote the macroscopic system of interest. Okay, but now then further let A prime denote its environment. Okay, so it can exchange energy, maybe even particles. We have to specify all those things, and so we are interested in questions about A, but we can't avoid A prime. So what we can see here is that the combination A star, which is A, the union, or A plus A prime, is isolated. Okay, so so the idea here is that even though A is not isolated, A star is isolated. So our postulates are applicable to A star. Okay, so for instance, so let E star,
Sure, but what is A star isolate from?
there's nothing, everything else is in A prime, that's all. The rest of the world, if you want.
Okay.
Let E star be equal to, say, so this is the energy in A and energy in E prime, be the energy. of macro state. Okay, for a moment we will not think. Excuse me. So then we can define something like this, right? Omega star of E star. This will be the number of accessible okay. So each of these are equally probable, but from this we would like to go back and ask. So if we are told, if you know something about A, then then we can. So we want to know something about A. So we have to see how to how to figure this out. Okay, so this will give you the total number of microstates. Okay, so let's ask one question. So okay, but E, I mean E plus some delta E, etc. Okay, so then this probability. So now how does it work? So we have to ask how many of these. So this will so there are so many such microstates. So the probability of this thing will go like omega of T Do you agree with this? So these are all the microstates. Is this normalized? Okay, so I'll stop here, check this, and we'll. If it's not correct, what is the correction that I need to do? Okay. So I'll stop here for today. And so next lecture we will see how to make use of A star to figure out what some statements about what we mean by saying A and A prime are in thermal equilibrium. We will see that has some implications, and then we will try to interpret that implication. Okay, so I'll stop here.
Sir, here constituents of star are interacting with each other. So, are we still assuming that non-interaction?
So yeah, I've written E star equal to E plus E prime. So I'm just saying that even if they're interacting, it's very weak. I'm ignoring interactions. So I'm saying that the total energy E star is the sum of those things. Otherwise, there would have been E plus E prime plus some interaction.
How did they get the idea of ensemble average? Is it like they tried it out and it gave correct results?
How to take ensemble average? Okay, so my knowledge of history is I don't think this was the way it was done first, but it eventually came down to this picture. Okay. So we already saw we were able to get some, using just some simple arguments, we were able to get some idea of some probabilistic distribution was there before. But I think it just goes back to Boltzmann, I think.
Okay, thank you.
Under what conditions are all microstates of a system equally likely?
Oh, I don't know the theorem. Some mathematical theorem. So your system should be mixing or chaotic.
Physically, what conditions must be satisfied so that all?
Physically is done. I mean, these are mathematical theorems. I thought you wanted that. So these are technical. I mean, these are hard theorems. This is not some. These are not simple theorems. I don't know their functions. I have never studied those things.
Sir, while
But, physical means it just says that the system is mixing enough. I mean, that's all. I mean, that's whatever I said is physical. Waving my hands. Physical usually means waving hands. So yeah, I have done that.
sir,
Sorry.
sir, while calculating energy, quantum mechanically, we are also ignoring the collisions.
Yeah, absolutely. I said that first. Yes.
Or in case of
Yeah.
statistical mechanics, we considered that things.
No, the point is that saying that in an ideal gas, it is wrong to say that there is. I mean, the energy is just that simple thing which we wrote, because there are collisions, and that is true even quantum mechanically. But doing the full quantum mechanics, including collisions, etc., is a big mess, and it's not necessary. It's not necessary. So all I'm saying is that collisions serve to make to lead to mixing, which leads you to a situation where all accessible microstates are accessed, and the postulate says that they have equal. They are once that happens and you reach equilibrium, all those things are equally bound. That's all.
Okay, sir.
Yeah, that quantum mechanical formula I wrote also is ignoring collisions, just like the free particle Hamiltonian that I wrote. But collisions are important for statistical mechanics because they do happen, they serve to, and like I'm saying, that is a requirement that is actually important for this, for the postulate to be applicable. Okay, any other questions?
When is the